Hi, we'll be starting the webinar in about 1 minute.
All right, good morning everybody, and welcome from the shores of Lady Bird Lake here in Austin, Texas. Well, actually not. We thought we'd try to improve the look of our Deminar set a little bit. We're here at Greg McMillan's live process control seminar and demo series, and we call these Deminars for short. Today's topic is PID control of true integrating processes, how to reduce the batch cycle time for temperature and pH loops by 25%. This broadcast is being recorded and will be available for future viewing. We'll be muting all but Greg's microphone, so please use the Q&A box and ask your questions of Greg, and I'll relay them verbally to him during the course of today's session. And we'd like these to be as interactive as possible, so fire away as those questions occur to you. With that, let me turn it over to Greg.
Yeah, thank you, Jim. Well, we're going to concentrate on true integrating processes. They occur quite a bit in batch operations, and they will almost be true integrators for some continuous processes that are very slow, and we saw that last webinar with the near integrating processes. And what we're going to do today in terms of speeding up the Setpoint response, it not only applies really to the true integrating, but also the very slow near integrating processes that we discussed in the last webinar. Again, this is sponsored by Emerson, Experiotech, and Mina. Experiotech is a local business partner in St. Louis, and Mina has their simulation technologies in St. Louis. And I have the help of Jack Ehlers in putting this together. Jack is a process control specialist at Monsanto in St. Louis. And the website is developed by Charlie Schleiser, and he's the IT consultant for Experiotech and Mina, and he has his own company, CS Design Co., and you can see his email address there. The Process Control Lab website, which we are continuously trying to improve, is available. And so let's get into it. This is me, and by now you know enough about me. President Obama was in Austin at the Gregory Gym on the UT campus, which is a very high-tech, sophisticated setup these days. And so I thought, well, what, going high-tech, what if a control engineer was president? So here we have this top 10 list. Top 10 reasons to elect a control engineer as president. Number 10, completely automated and remotely controlled combat, so that it's more like a video game. How about dynamic programs? Models of the economy, high fidelity models possibly. No overshoot of the budget. Real-time optimization of manufacturing. Regulatory control of financial markets. Feed-forward control of Congress. Good luck there. Model predictive control of energy. A nuclear reactor in every home. With my undergraduate degree in engineering physics and having mostly nuclear submarine captains in my class, I can really appreciate that. And the number one reason is a computer in every pocket. Well, today we're going to do demos of control loop opportunities to reduce fed batch and startup time. By fed batch, we mean that there actually are control loops whose set points are being manipulated rather than just doing on-off charges. So we got flow loops, and the set points of those flow loops are manipulated by, say, temperature loops or pH loops. We're going to look at the effect of PID on error structure to see what that does, and we're going to seek to maximize the kick and the bump of the controller output for a set point change to get us to move a lot faster, particularly in the beginning, to approach that new set point. The overdrive, the driving of the output past the resting point, is essential for getting slow loops, which is what we're talking about for vessels such as what we're trying to do in batch operations and startup operations, and bring temperatures and set points to their optimum set point as fast as possible. The temperature and pH set point change must be made with the PID in the auto mode in order to get that bump and kick. Set point track PV will generally maximize the set point change because you'll be starting out with a set point that's typically pretty far from the optimum. It may just be reflect very beginning ambient conditions, and hence you'll get a big kick and bump. However, if you retain the set point from the last batch or startup, this is going to minimize the kick and bump. We're going to look at set point feed forward. For low controller gains, controller gain that is less than the inverse of the process gain, set point feed forward is particularly useful. For this case, the set point feed forward gain is the inverse of the dimensionless process gain minus the controller gain. Today, we're not looking at that situation. We're going to be looking at integrating processes, and we are going to have a controller gain that's greater than 1. For slow, self-regulating, continuous processes and slow integrating, for example, batch processes, even if the controller gain is high, the additional overdrive can be beneficial for small set point changes that normally would not cause the PID output to hit a limit. So we're going to use set point feed forward to help get that output closer to its limit. If the set point and controller output are in engineering units, the feed forward gain must be adjusted accordingly because, again, the PID controller works in percent. The feed forward action is the process action, which is the opposite of the control action. A very important point, because if you don't have the feed forward action right, it's going to do more harm than good. So you got to also take into account the valve action. In other words, for a reverse control action, the feed forward action is direct, provided the valve action is increase open, or the analog output block, I to P, or positioner reverses the signal for an increase closed valve. The last demo today will be for the full throttle bang-bang control. And here, the controller output is stepped to its output limit to maximize the rate approach to the set point. And when the projected PV equals the set point, less a bias to allow for errors, the controller output is repositioned to the final resting value. The output is held at the final resting value for one dead time. For more details, you can check out the Control Magazine article, Full Throttle Batch and Startup Response, and we have the link there for you. Now, some important features of this is a dead time block must be used to continuously compute the rate of change so that you see new values of the PV immediately as a change in the rate of approach. If you were to do this calculation periodically over an interval so that you have discontinuous values, you would not immediately see the change, and it could possibly even be delayed. The true change could be delayed by up to the dead time, and you don't want that. You want to immediately see a change in the rate of approach to set point, so it's important to use that dead time block. If the total loop dead time is used in the dead time block, the projected PV is simply the current PV minus the output of the dead time block, which gives you a delta plus the current PV. If the rate of change, the PV is useful for other reasons, for example, we saw in the last seminar for near integrator tuning and also for true integrator tuning, then you could go ahead and compute the rate of change of the PV is simply equal to the delta PV divided by the dead time. If the process changes during the setpoint response due to reaction, say, or evaporation, the resting value can be captured from the last batch or startup. If the process changes are negligible during the setpoint response, the resting value can be estimated as the PID output just before the setpoint change for an integrating batch process, which is what we're going to do today. Otherwise, the PID output just before the setpoint change plus the setpoint change divided by the process gain can be used for a self-regulating continuous process. We have another situation where for self-regulating processes such as flow, where the loop dead time is approaching or is less than the largest process time constant, the logic can be revised to step the PID output immediately to the resting value. The PID output is held at the resting value until the process fully responds, which would be the T98, or the time it takes to get to 98% of the response, and that can be estimated as the dead time plus 4 time constants. So here's something else that could be done for self-regulating loops that are dominated by dead time. An integrating response is different in that it never reaches a steady state. We look up here and it's still ramping. Also, if we're doing this test in manual, we can be assured if we look closely enough that the process is probably ramping. Now, if we just put it in manual and we were doing tight control, the ramp rate may not be that visible. But to take into account that ramp rate is very important. So when we compute the integrating process gain, we're really going to look at the change in ramp rates before and after we made the change in controller output, which occurred right here. Once we see a change in ramp rate, we can then use that to estimate the dead time, the observed dead time in the process. And again, it's important that we use percent. So instead of process variables that are in engineering units on your trend charts, I'm making the important point that you have converted that to a percent controlled variable, which I call CV. Similarly, you know, the PID controller output can have engineering units, but what the algorithm is using, the PID algorithm is using, is a percent controller output. So instead of saying out for PID output, I say CO for controller output to denote that we're working in percent. This shows you all the dynamics in the loop. The important thing today is we're going to be looking at the integrator process gain, and that is the product of the valve gain. And then we can look at the integrator like it would be a near integrator, and I do this conveniently for the process control labs as simply the process gain divided by the largest process time constant. So we take the process gain here and divide it by the largest process time constant, and that gives us the integrating factor there. We then have to remember to multiply it by the measurement gain, which is basically just 100% divided by the span. Going back to the valve gain, that's going to be the slope of your control valve characteristic, and so it's going to be in terms of flow, change in flow for a percent change in signal to the valve. Anyway, we've got, it's important to get that integrating process gain, and then we want to get the total observed dead time. Where does that come from? Well, If you wanted to look at how we get that from these loop dynamics, we would first sum up all the pure dead times and delays here in the loop, and then we would sum up all the small time constants or lags in the loop, and that would give us the total observed dead time. Hopefully, again, the largest time constant is right here in the process, so that it's going to slow down the load upset. Because if the largest process time constant was here, we wouldn't get any slowing down, which is very important of the load upset. Furthermore, if the largest time constant was here in the lag, we would be seeing a very filtered, smoothed out version of what's really happening. Here's the nomenclature for the equations we're using today. This shows the PID structure for the ISA standard form, and that's the most prevalent one today in a DCS. And notice that we have some multipliers here for the set point. They're called set point weighting factors, and if we take the set point here and trace the path to get the proportional mode here, we see that there is a set point weighting factor, beta, and that's important as we're calculating the error here for the proportional mode. Similarly, there is a set point weighting factor for the derivative mode used in calculating the error, and that's important for the derivative calculation. So if these factors were equal to 0, we would have, for a set point change, we would have no effect on the proportional and derivative mode contributions to the controller output. And that's one of the things we're going to be looking at today. So in the delta V DCS, you actually have 8 choices here, and what's probably the default, most likely, is PI action on error and derivative action on PV, because some people don't want a bump in the controller output from a set point change, and they just want it to act on the process variable. We're going to start out to show you what would happen if we had only integral action on error, so that both the weighting factors were 0, and that meant that proportional derivative action was only on the PV. And then we're going to switch to getting the PID action on the error, and here now we're going to have both the weighting factors equal to 1, so we'll get the maximum kick and bump from proportional and derivative modes to get us to going to set point faster. So let's look at the contribution of each PID mode to a set point change. And so we're looking initially at the kick from the proportional mode, the delta CO1, again we're working in percent, and so we get this initial kick here right away. Then we get a bump from the filtered derivative mode, and the important thing is that in DCSs today, there's automatically a filter that is about, whose time constant is about 1/8 of the rate time setting. If you didn't have that, this would be truly a very rapid and narrow spike. Now, when we look at the trend charts, this bump may look like a spike just due to the time span that we have on the trend chart. But if we were to zoom in and look at a much smaller time span, we would realize this is more like a bump and had enough resolution, actually, of the trend chart. And then we've got the integral action going on, and when the integral action gives us another contribution from its ramp that is equal to the initial kick, and that's occurring right here. So the change in controller output number 2 is equal to what we got from the kick, and change in controller output number 1. We have repeated the contribution from the proportional mode, and this time for that to occur is the seconds per repeat. Now today we've dropped the repeat and we just call it seconds, but the original definition in the thinking of this was that it is seconds per repeat. How long does it take for the integral mode with its contribution to repeat the kick that you got from the proportional mode? Okay, well, there's a lot of equations here, and don't really need to get into them, just the fact they're different, a little more complicated than they are for self-regulating processes. These equations are in adaptive tuning software like Delta V and Sight. What we want to take a look at, first of all, though, instead of the lambda that we have for self-regulating processes, that is the closed-loop response time, we now have a lambda that is the closed-loop arrest time for a load disturbance, which means how long does it take after a load disturbance before you turn it around. We still have this lambda factor, but really we're dividing that by the integrating process gain to come up with this lambda that is the closed loop arrest time, and we're using that in equations. Now again, we've defined the integrating process gain this way as a change in ramp rate divided by change in controller output, making sure we're always using percent rather than engineering units. Then we have a little more complicated equation here for the controller gain and also for the integral time. The derivative time, if we can identify the smaller secondary lag, is pretty straightforward. You should set the derivative time equal to that small secondary lag. What's neat about these equations is they automatically enforce this relationship where the product of the controller gain and integral time or reset time is greater than 2 divided by the integrating process gain. If you don't do this, you can get into slow rolling oscillations. Now, you may not see this if you got a lot of things going on in terms of disturbances, set point changes, but given that there is some quiet period, what's going to happen is the loop is going to just keep rolling with oscillations, and the amplitude of the oscillations get worse as you get farther and farther below this limit here expressed. And it's confusing. A lot of people make the wrong decision. They see these slow rolling oscillations, and what do? They say, oh, I must have too much controller gain. So they reduce this, and this actually then drives it further below the limit, and it causes the oscillations to get worse. A very common problem with integrating loops, there's kind of a window of allowable controller gains where you can get into trouble by having the controller gain too slow, by getting into these slow rolling oscillations, and if you have the controller gain really low, they're almost looking like approaching equal amplitude. The damping is very slow, and you can get into a lot of trouble over a long period of time, particularly noticeable level control on distillation columns. So this automatically prevents that from happening. So let's look at today's example of the dynamics. We're going to have a secondary and primary process gain of 1. We're going to have a small lag in the secondary process of 2 seconds. We're going to set up the primary process lag to be relatively large, at least for a demo. In real life, this would be 3 or 4 orders of magnitude larger. And we're going to set up, for this demo anyway, a pretty large dead time. And so the integrating process gain, using this calculation of taking, the process gain, dividing it by that large time constant, gives us a value of 0.01% per second per percent. And if we consider a lambda factor of 1, which is actually the lowest you get out of the auto-tuner, then we end up with these values here of an integral time, a reset time of 210 seconds, a controller gain of 1.7, a derivative or rate time of 2 seconds. And if we look and make sure we're satisfying this inequality here, prevent slow rolling oscillations, we say yes we are. We're coming up here with about maybe 360, which is certainly greater than the 200 on the right side here. And we're in good shape in terms of preventing those slow rolling oscillations. So let's go into the first demo, and we're going to use that PID structure 3 that is not particularly good for Setpoint Response. And so our objective is actually show that slow Setpoint Response that occurs from just using mostly interval action. So we're going to enter in the tuning settings first to make sure that tuning is set up before we create this disruption of changing the process. Then we're going to set the process dynamics. Once we do that, we're going to change the process type to integrating. We're going to choose a different controller structure and finally make a set point change. So I'm going to go to my desktop. Okay, when you go into the Process Control Lab, you should be in the main screen here. And we're going to be working with a single loop here. And the first thing we want to do is to bring up the faceplate of the controller and the detail display. And we want to change the tuning. Notice the big increase in reset time, and this is typical for integrating processes. One of the common problems people have is they've got too small of a reset time and they're getting into reset cycles. Now let's go ahead and change the process, and we'll set the the delay to 9 seconds, because we already have 1 second in the secondary process delay. We're going to set the big lag here in the primary process to 100 seconds for both the increasing and decreasing directions. Now we've got the process set up with the dynamics we want, because we're going to keep the delay here of 1 second in the secondary process, and also keep the small secondary time constant at 2 seconds. So now we're ready to switch to integrating. And we want to change the controller structure from its default to this one where we get interval action on error. So on the set point change, we're only going to get that interval action. When it makes that structure change, it temporarily takes the controller out of service. So let's bring up a trend chart. So here we go. We've got the Loop Lab 1 trend chart up, and we'll go ahead and make a set point change. And let's look at what's going to happen here with this trend chart. We'll decrease the time span a little bit here. And so here we've got the set point change. We're not getting much here of a controller output change. We've certainly got no kick or bump. So we're relying upon interval action to ramp up the controller output. And you can see that the process variable, because of the dead time, but also the very slow ramp up, hasn't done much. While we wait for this very slow response to develop, we'll go back and take a look at some presentation slides of other techniques that we're not going to cover today, but are important for reducing batch time and startup time. So other control loop opportunities to reduce batch and startup time, fed batch. We're looking at the possibility of an output lead lag, a lead lag in the controller output or in the digital positioner, that is an option in the DVC, the digital valve controller. It can kick the signal through the valve deadband on stiction and get past split range points and make a faster transition from heating and cooling and vice versa for those split range applications. A lead lag can potentially provide a faster set point response with less overshoot when analyzers are used for closed-loop control of integrating processes. When combined with the enhanced PID algorithm, PID Plus, that was described in Deminar 1 and also in a very recent white paper, and we got the links there for that. Also, you can do dead time compensation. The simple addition of a delay block with a dead time set equal to the total loop dead time that's in the external research signal for the positive feedback implementation of integral action, which we use in Delta V, as described in Deminar 3 and for the dynamic reset limit option. And you can take a look at that Deminar to see how that positive feedback implementation and dynamic reset limit is actually very useful for a lot of things, and here it would allow dead time compensation. And we have that capability in process control labs, and that will be a future Deminar, is to just simply turn that on. We have the dead time block inserted, and it's just a matter of entering the dead time. The controller reset time can be significantly reduced and the controller gain increased if the delay block dead time is equal to or slightly less than the process dead time, as studied in the advanced application note. And again, there's a link for that. So this is kind of interesting. It's not what you normally think of for control loop tuning in terms of it'd be better maybe to overestimate the dead time. Here it's a little bit better. Well, it is better to slightly underestimate the dead time, and the application note shows that. Then we have feed maximization, and we can do that for by means of monopredictive control described in application note 1. Or we can do override control, which we're going to show on the next slide, to maximize feeds to the limits of operating constraints, the valve position control. In other words, there is a maximum possibly vent valve position, overhead condenser valve position, or jacket valve position, and we want to get to that maximum position that still has sufficient sensitivity per the installed characteristic. Alternately, the limiting value can be set wide open and the feeds throttled for temperature pressure control. For pressure control of gaseous reactants, this strategy can be quite effective. However, for temperature control of liquid reactants, the user needs to confirm there's no inverse response. In other words, does the temperature go in the opposite of the final direction from the addition of cold reactants to an exothermic reactor? Also, the lag from the concentration response in series with the temperature response can cause control problems. All of these methods require tuning and may not particularly adept at dealing with fast disturbances unless some feed-forward action is added. Fortunately, the prevalent disturbance, that is a feed concentration change, is often slow enough due to raw material storage volume to be corrected by temperature feedback. Lastly, one of the other control loop opportunity we're going to look at today in the slides anyway, but not with the demos, is a profile control. And if you have a batch measurement that should increase to a maximum batch endpoint, for example, a maximum reaction temperature or product concentration, if you're fortunate enough to have analyzers, the slope of the batch profile of this measurement can be maximized to reduce the batch cycle time. So you can check out this chapter, Direct Temperature Rate of Change Control that Improves Reactor Yield, and a funny thing happened on the way to control room, which is an ebook with that link on my website. You can also go to the Control Magazine article, Unlocking the Secret Profiles of a Batch Reactors, and get more details there on profile control. This is the example of the override control that I worked with that was very successful and consistently reduced the batch cycle time by more than 50%. And it had several valve position controllers. For example, We had the first one here on the coolant jacket was maximizing the coolant valve position, but keeping it on as part of the characteristic that still had sensitivity. Then we also had a valve position controller here that was maximizing the cooling tower water to the jacket, but still keeping it in a very controllable position. We had another valve position controller here maximizing the vent valve position. And all of these were important because this reactor was operating at over twice nameplate. As a result, the cooling tower systems and vent systems hadn't kept up with it, and consequently during the batch you get into high temperature, high pressure shutdowns that would temporarily stop the batch, interrupt the batch, and what this override control did was eliminate those shutdowns and just smoothly throttle back on the feeds because you were using a low signal selector here. And so all of the valve position control outputs went through a low signal selector, and that became the set point for the lead flow controller that was then through a ratio setting the follower feed. And it's just showing a second feed here, but there could be several more feeds. We have another valve position controller that says, hey, if for some reason we are not at the maximum feed rate here, and we can do something maybe to then raise the reaction temperature to give us a higher reaction rate. And now, if you get into pure batch and startups, there are sequences, and startup sequences can be done with batch software, and in a way it is like a batch operation. So a lot of the things that you do to minimize the time of that sequence in a batch operation are applicable here for the sequences in a startup operation of a continuous plant. And I'm not going to go into these in detail. Actually, Jack Ehlers is much better, has more experience in each one of these possibilities. So if you are interested, I can forward your question to Jack. So we should be getting some response, but so we want to move on, though, and show the faster response from the addition of the kick from proportional mode and the bump from derivative mode. But first we will look at the slow response we got for structure 3. Then we're going to choose controller structure 1, so we get PID action on error, which means the set point weighting factors are both 1. And we're going to make another set point change to see how much faster we can get the set point. So I'm going to share my desktop. And you can see here we finally did reach set point, but it sure took a long time. So let's see what we can do by changing controller structure. And choose controller structure number 1, PID on error. Now we will make another set point change. In this case, we will go back to 50%. And notice we are getting a nice bump and kick from the proportional and derivative modes. And now we're getting the correction to that through feedback action, and you can see we've got a faster approach to set point, so it looks like we are going to do better, but this is still going to take some time to develop. So let's go back and look at our presentation and see what else we can learn about opportunities. So let's consider the model predictive control of batch profile. And here we show the models that were identified for biomass growth rate in terms of how did dissolved oxygen and how did glucose concentration affect that. And notice there isn't that much effect of dissolved oxygen, but significant effect of glucose. And here we're taking the biomass concentration measurement and computing a rate of change so that we get a biomass growth rate. So in general, what we're doing here is computing rates of change that the model predictive controller is going to use as its control variable. So here we're going to control production rate. So we take a product concentration measurement and compute the rate of change of that. And we model then the effect of dissolved oxygen on it, and we can see there's a little bit of an effect, but the big effect is really from glucose concentration. This shows the model predictive controller, how it did its job for a batch. And kind of the neat thing about this is that it automatically put itself into auto and captured the highest product formation rate. So it was looking at the rate of change of product concentration, and when it reached the maximum, it said, wow, that looks like a good set point, and let's go in automatic and keep that. Now, you could have had it set up to maximize the biomass growth rate, so when the rate of change of biomass reached a peak, you could have captured that and said, that's what I want to really maintain as a set point. But, really what you want to do is to maximize the product concentration, not biomass concentration. So that's why the controller waited till there was a peak in product concentration formation rate. And then as the batch went on, it manipulated the dissolved oxygen, it raised it, and it lowered the substrate, and as a result it was able to keep the product formation rate pretty close to its maximum, and it had the highest priority. It let the biomass growth rate decrease because that wasn't as important. So we're going to show now how batch cycle time can be reduced by the use of Setpoint Feedforward. But first, let's look at the Setpoint response for Structure 1. And after that, we'll see what we can do with Feedforward by setting the Feedforward gain equal to 2 and making another setpoint change. So we'll share my desktop. And here you notice, wow, it got to set point a lot faster, and the time it takes for it to cross or get close to set point, to first get close to set point is the rise time. And then how much it goes past the set point here is the overshoot. And then how long does it take before it gets back to the set point? And you can see here the interval action is trying to bring it back, and it will get back to set point. And when it gets close to being at set point, that's the total time since the set point change is the settling time. It's not quite back at set point, but we're going to go ahead and set up for a feed forward, and we can simply do that by entering a feed forward gain here. In other words, the process control labs right now say, well, if you got a 0, it's not going to do anything. So if you enter a value now, we will have set point feed forward gain. And we'll make a set point change here from 50 to 60%. And we'll see what that does. We actually pretty much hit the high output limit momentarily. We may not capture that on the trend recording. But what we will capture is the fact that we are getting a bigger change in the controller output as a result of adding in the set point feed forward. And hopefully this will get us to set point a little bit faster. Well, while that's happening, we'll go back and we'll look at more about model predictive control of batch profiles. This could also be useful for profiles for startup responses, in that there may be an optimum rate of approach to the set point for continuous process startup as well. Well, let's look at the results here that we have for a bioreactor, and if we look at product concentration here, and look first what normally happens for a basic fed batch, where we're keeping, say, the feed rates of air or the dissolved oxygen concentration set point constant, and the glucose concentration is just constant, or the glucose feed rate is constant. We end up with a situation where this profile, the slope of it, starts to decrease here. And as a result of the slope decreasing, it takes longer for it to reach its endpoint here. By going to model predictive control of this fed batch, we have the model predictive controller in auto. Notice that now the slope looks like it's the same. It's kept basically a constant slope, so it takes a lot less time for reach the endpoint. Now, if we look at the biomass, we find that there may be some improvement in terms of keeping the slope constant, but really that wasn't the objective, and as a result, it's not that noticeable. The big improvement was in the product concentration. And that has important implications in terms of repeatability of the batch, which makes it also easier to predict where the batch is going to end up. I just had a very simple prediction method here, and as a result, for the basic fed batch, when I was just going to try and predict batch cycle time, it made an error in that prediction, and really the error wasn't eliminated until the end. Now, if you look at the result of having the MPC in auto, at a certain point through the batch, when it says, hey, I know what's going on, it makes a drastic correction of prediction, and it gets very close to what the final cycle time is. Also, if you're looking at yield, it has some trouble doing that and only really homes in on it at the end, whereas again, right here at this point, it recognizes a dramatic improvement in yield, and that's principally the result of reducing the glucose concentration, and the high glucose concentration, besides wasting raw material, was actually inhibiting the product formation. Okay, well, let's show the bang-bang control, and we're not going to do that by the use of a lead lag. We're going to use it by the use of bang-bang control. So there's a mistake here in the objective. We're not going to be doing that lead lag. We're going to use bang-bang control. Sorry about that. First, we're going to look at the Setpoint response for Setpoint Feedforward. Then we're going to set that Setpoint Feedforward gain to 0. Then we're going to set the bang-bang bias at 4%. And make a set point change from 60 to 50% and see the improvement. So I'll share my desktop. And here you can, if you take a close look, you would probably see that it has gotten to set point a little bit faster, so the rise time is less. The overshoot's a little bit less, and the settling time is less. So let's go and now try out bang-bang control. And we're going to do, first of all, eliminate the Setpoint Feedforward. So we're going to enter Setpoint Feedforward gain of 0. Then we're going to put in a bias, and because this is such a fast integrating process, and the calculation is done in a module that only executes every 2 seconds, I have to have a significant bias here in order for it to realize the effect of the control module execution time and take that into account. And so we're going to enter a 4% bias. And now we're all set up for bang bang control, and we're going to make a set point change to 50%. And notice we go to our route, and it says, wow, we're going to go to the limit, 0%, and we're going to hold it there, and hold it there until we see the process variable is approaching the set point. And when it gets to where we think it's going to end up at the set point, we then hold the resting value, which is the value right before the set point change for this integrating process. And then we hold that for 1 dead time, and then we go to auto, and we should be hopefully in good shape. So let's take a look at the response here. Well, we can see, particularly if we zoom in here, we can see that we went to the output limit and held it there until it thought the projected PV was going to be at set point. And then it said, okay, let's go to the resting value. It then held it at the resting value for at 50% for about 1 dead time. And then it said, okay, I'll release you back to automatic control to correct for any things we didn't really know about. So you can see quite an improvement there from the bang bang control in terms of how fast to get to set point, the rise time. The settling time is essentially the rise time. There's very little overshoot, and we're definitely in good shape. Let's go back and finish up this seminar. This summarizes hopefully what we saw today. With structure 3, the rise time was about 8.5 minutes. The settling time was about 8.5 minutes because there was really no overshoot. So the settling time and the rise time were the same. And then we looked at structure 1, and we were able to reduce the rise time to 1.6 minutes, but due to the overshoot of 1.7%, it took about 7.5 minutes for it to settle out close to set point. We then added the feed forward to structure 1 and reduced the rise time slightly, the settling time slightly, and the overshoot slightly. The big improvement occurred when we added bang bang control, and here we reduced the rise time to half a minute. That was the settling time, and we reduced the overshoot to about 0.2%. So, help us improve these seminars.
Thank you very much, Greg. Before we open the floor to questions, I'd just like to make a couple closing comments. First, I'm going to send or publish a link to a one-question survey right here with this URL so you can cut and paste. And we'd really appreciate any thoughts or comments you have on today's seminar. Let's go to the next one. And our next seminar is going to be August 25th, Wednesday, same time here, 10 a.m. Central U.S. Daylight Time, or 1500 Universal Coordinated Time. And Greg's topic is going to be PID control of runaway processes. The other point I'd like to make is the recording for today's session will be posted on our blogs, Greg's modelingandcontrol.com and my Emerson Process Experts blog here this week. So feel free to share it with your peers and friends and family and everything else. And with that, I'll be looking for your questions. Thanks.
By the way, we will make available the module for Bang Bang Control for you to try out on Delta V, and we'll put it out in version 8, and you can migrate it to whatever version you have. And of course, with anything new, you need to be careful and monitor it closely, and you might just see what it's asking to do first before you actually try it out, and it could be quite impressive, the improvement.
Okay, we'll leave things open for about another minute. I'll be looking for your questions. Thanks. Oh, we've got one here. Greg, is there any impact on CPU or controller load on a real system?
No, we don't see any. I started to put on a screen print the blocks used, and I said, well, we're probably going to refine and expand the capability, and so I didn't show you the configuration, but it's very minimal, and so we're just talking about an expression block plus a dead time and filter block and subtractor block, and you know, it's negligible. And the reason I had that module set for an execution of 2 seconds was because it's doing a lot of other things, and really it needed to see the effect of what it had asked the PID to do. And so the PID modules are executing every 500 milliseconds, and the control module that sets up all the scenarios is executing every 2 seconds. But actually, as I looked at, you know, what it takes to execute, it's doing its job in a couple of tenths of a second. So I guess really the only reason I have it executing 2 seconds is so it can wait for the PID to go through its mode changes and do its thing before it makes another decision. So the loading is negligible.
Sergey, I see your question. Do you want to relay it audially or put it in the Q&A box? Oh, I see it here. Okay. Greg, could you please elaborate a bit on the integral delay option?
Oh, the dead time compensation. Yeah, that's a pretty neat little deal there. Very, very simple in terms of inserting a dead time block, and I guess there's no problem with me like showing you, for example, how we're doing it here.
You have to switch over.
Oh, and I have to switch over. Sorry, I'm going to share my desktop here. And I'll just show you here the PID module. So for us to simulate the use of that dead time compensation, all we did was insert this dead time block, and we do it by taking the backcal out of the AO block and running it into the dead time block. We got to make sure we set this dead time pretty accurately to be equal or slightly less than the total loop dead time, and then we wire that output. And if you were just doing dead time compensation, you would wire it into the backcal in. Here, since we're simulating PID Plus in version 10, and PID Plus with its capability for sample data or discontinuous measurements is really available in version 11, we put in a composite block. And so that wouldn't normally be there if you just wanted to do dead time compensation.
And the follow-up is there any relation to the Smith predictor?
Well, yeah, if you were to set both accurately, they would give similar results. However, the Smith predictor requires that you set the process gain and the process time constant accurately. Well, here, you don't have to set a process gain and process time constant. There's only one parameter to set, and that's the dead time. So it's a simpler implementation and adjustment. Again, though, in order to get the performance improvement, you're going to have to go ahead and tune the controller more aggressively to take advantage of the fact that it now knows the effect of dead time. And so if you go ahead and tune the controller with a much faster reset time and and even a higher controller gain, you're going to get a performance improvement for those systems where dead time is significant and you know what the dead time is. And you can get that dead time from the use of an auto tuner or Delta V Insight.
All right, how's that for precision? We're right at 11 o'clock here Central Time, and I think we'll wrap it up with that. I want to thank everybody for joining us this morning and thank Greg for sharing his expertise with us, and we look forward to seeing you and everyone else on the 25th, so spread the word, and we'll see you in a few weeks.